So History of Math, Lecture 17, and there was a question about homework 7. Which problem?
Number 3.
Okay. All right, so let's start the easy way. If you look at the book in the text, on page 203, it's giving another proof of the divergence of the harmonic series. So what it says in the book is 1 plus a half is bigger than a half plus a half, which is 1. Right? Does that look okay?
Yes.
And 1 plus a half plus a third plus a fourth is bigger than 1 plus a half plus a fourth plus a fourth, because I'm replacing a third by the smaller number, which is a fourth. And a fourth plus a fourth is a half. So this is 1 plus 2 over 2. Actually, I could have here just left this as 1 plus a half, which is 1 plus a half. This is 1 plus 2 halves. If I add the next 4 terms, they'll go from a fifth up to an eighth, right? There are 4 terms, a sixth, a seventh, and an eighth. And each of these terms, these 3 terms, are all bigger than an eighth. And each of these 2, this is bigger than a fourth. So this is bigger than, you see, this and this was 1 plus 2 halves. And this is bigger than 4/8, which is another half. This is 1 plus 3 halves. And the problem is, so this is basically exactly the homework problem. So the homework problem had 2 parts. Prove that if you take the sum from n equals 2 to the k minus 1 plus 1 up to 2 to the k of 1 over n, this is bigger than a half, right? This is what you have to prove for all k greater than or equal to 2. So a good way to understand the good way to attack the problem is look at like the simplest cases. So in case k equal 2, what does this say? This says the sum from n equals 2 to the 1 minus 1 plus 1 up to 2 to the first power 1 over n. Let's see. 2 to the 1 minus 1 is 2 to the 0, which is 1. 1 plus 1 is 2. This is the sum from n equal 2 to 2 of a half. Sorry, of 1 over n. That's just 1/2. Right? Right? I mean, let's look at k equal 3. Maybe I should have started at k equal 3. When k equal 3, the sum from n equal 2 to the 3 minus 1, 2 squared plus 1, up to 2 cubed of 1 over n. Right? This means this is the sum from n going from 5 up to 8, 1 over n. From 5 to 8, you have 4 terms, and the smallest is 1/8. So this is bigger than 4 times an eighth, which is a half. And when k is equal to 4, this is the sum from n equals 2 cubed plus 1 over up to 2 to the fourth 1 over n. 2 cubed plus 1 is 8 plus 1 is 9 up to 16 1 over n. Here you have 8 terms, and the smallest is 1 over 16, so this is greater than 8 times 1 over 16, which is a half. And after you see this pattern, you might say, okay, well, what about the general case? So the general case is the sum from n equal 2 to the k minus 1 plus 1 up to 2 to the k of 1 over n. So if you look at the number line, the integers from 1 up to 2 to the k, when you've gone halfway, that's 2 to the k minus 1, right? Like that's half of 2 to the k. And the next number is 2 to the k minus 1 plus 1. From 1 to 2 to the k minus 1, you have 2 to the k minus 1 numbers. From 2 to the k minus 1 plus 1 to 2 to the k, you also have 2 to the k minus 1 numbers. It's just like in this case, when you're summing from 5 to 8, you have 1, 2, 3, 4, 5, 6, 7, 8. From 5 up to 8, you have 4 integers. From 9 to 16, you have 8 integers. Right? And from 2 to the k minus 1 plus 1 up to 2 to the k, you have 2 to the k minus 1 integers. So you have 2 to the k minus 1 terms, and they're getting smaller because the denominators are getting bigger. So this is bigger than the number of terms times the smallest term, 1 over 2 to the k. 2 to the k minus 1 over 2 to the k is a half. So this is exactly what is done on page 203. Is that clear, or do I have to? I'm happy to explain it more if I have to.
No, that's clear, but also, if you don't mind explaining, I was very confused on the theorem of harmonic series diverging to infinity, of how the book explained it. Um, where they set h to 1 plus and plus 1
Okay.
half, 1/3,
All right,
and
let me finish
such.
this because this is only
Okay.
half of problem 3. Right?
Okay.
Problem 3 is another proof. That's what they're given on page 203 also. It's another proof that the harmonic series diverges. So what I just proved is that summation 1 over n from n going to 2 to the k minus 1 plus 1 up to 2 to the k is bigger than a half. So then I want to look at the series from 1 up to 2 to the k of 1 over n. So this is the first 2 to the k terms of the harmonic series, all right? I mean, this is 1 plus a half plus a third plus a fourth plus a fifth up to 1 over 2 to the k. This is the first 2 to the k terms of the harmonic series. And if you look at the numbers from 1 to 2 to the k, the integers, you have 1, you have 2, you have 3 and 4, you have 5 up to 8, you have 9 up to 16, and so forth. You can like put these in blocks of 2 to the k numbers. The last block would be from 2 to the k minus 1 plus 1 up to 2 to the k. So this sum is 1 plus a half plus, let's say, the sum of 1 over n, from n going from 2 to the k minus 1. Oh, sorry. Let me use a different. This is a sum, let's say, from j going from something up to k. And for each j, this is the sum of 1 over n from 2 to the j minus 1 plus 1 up to 2 to the j. Right? That's exactly the sum with k replaced by using the letter j instead of k. And I want this is from j equal to up to k. Right? I'm just taking these 2 to the k numbers and I'm writing them as in k blocks, 1, a half, then the next 2 numbers, like when j is 2, this is from 3 to 4. When j is 3, this is from 5 to 8. When j is 4, this is from 9 to 16. It's just, this sum is exactly this. But each of these is bigger than a half. So this is bigger than 1 plus a half plus k minus 1, that's how many terms there are, times a half, which is 1 plus k over 2. And this implies the harmonic series diverges, because as you add up the terms of the harmonic series, when you have the first 2 to the k terms, it's bigger than 1 plus k over 2, and this goes to infinity as k goes to infinity. So this is one more proof of the divergence of the harmonic series. This is a 14th century proof by Nicole Oresme. So this is not Bernoulli's proof. This is not the great theorem in this chapter is that the harmonic series diverges. And the proof that's given in that is the first proof is Bernoulli's proof, but there are 2 or 3 other proofs, and this is one of them. Okay. Now, if you want, I can also go through Bernoulli's proof, which is the one that's given in the greatest detail. It's up to you.
On the exam, we're allowed to use any proofs.
Well, the rule in the exam is to answer whatever question is asked. So if the question is prove the divergence of the harmonic series, you can use any proof, including the proof which I haven't done that was in Math 176, which involves an integral. If it says give Bernoulli's proof, then you have to give Bernoulli's proof. So, right, so I haven't made up the exam, so I don't know what questions are going to be on it yet. Though I might say that in the history of math class, it's enough to know any one of these historical proofs. So I probably would not insist that you give Bernoulli's proof. I'm not, so then I won't do Bernoulli's proof. I just want to recall that
This might answer your question.
Aye.
According to airnow.gov, Short Hills, New Jersey
Aye.
has no air quality alerts today. The
Aye,
air quality
aye,
is
aye,
good,
aye.
with an air quality index of 30.
All right. Recall. So Bernoulli's proof uses the convergence of the series of reciprocals of the triangular numbers. So recall the nth triangular number
Calling Triangular Wave Technologies.
Hey, oh my God. What is going on here? It's the nth triangular number is the number of dots in a triangle that you build up by successively adding another row to a triangle. So the nth triangular number is 1 plus 2 plus 3. It's the sum of the first n integers. And this you have to know is n times n plus 1 over 2. So if you list the triangular numbers, when n is 1, you get 1 times 2 over 2 is 1. When n is 2, 2 times 3 over 2 is 3. When n is 3, 3 times 4 over 2 is 6, and so forth. And so one of the Bernoullis proved that the sum of the reciprocals of these numbers, this infinite series, summation n goes from 1 to infinity, 1 over n times n plus 1 over 2, which is the same as summation 2 over n times n plus 1, and goes from 1 to infinity. And I can take the 2 outside, that's 2 times summation 1 over n times n plus 1. This series converges. Right? And the proof of this was to observe that 1 over n times n plus 1 is exactly equal to 1 over n minus 1 over n plus 1. So you have this algebraic identity. So if you're looking at the series summation 1 over n times n plus 1, n goes from 1 to infinity, that's the same as the sum from 1 to infinity, 1 over n minus 1 over n plus 1. And if you start to write this out, you see what's going on. When n is 1, you get 1 minus a half. When n is 2, you get a half minus a third. When n is 3, you get a third minus a fourth. When n is 4, you get a fourth minus a fifth, and so forth. And if you look at this, you see there's a lot of cancellation. Minus a half plus a half cancel. Minus a third plus a third cancel. Minus a fourth plus a fourth cancel. Everything cancels except this one at the beginning. So this series is equal to 1, which means that the sum of the reciprocals of the harmonic series is 2 times this sum is 2. So this is one of the Bernoulli brothers' results. The harmonic series diverges, and that is the sum of the reciprocals of the positive integers diverges. But if you take the sum of the reciprocals of the triangular numbers, that converges to 2. And when you look at the sum of the triangular numbers, it suggests you might also look at the squares. I mean, the squares geometrically are the number of dots, like there, 2 by 2 square, you have 4 dots. And if you extend it, a 3 by 3 square, you have 9 dots. And if you extend it, you get 16 dots. So you know the squares are 1, 4, 16, 25, 36, 49, and so forth. And the question is, does summation 1 over n squared converge or diverge? And if it converges, then what is it equal to? What is its limit? Or its sum? What is the sum of this infinite series? So one of the Bernoullis observed, compare this series to the triangular series. So in this series, you have 1 over n squared, which is positive. In the other series, you had 1 over n times n plus 1 over 2. And Bernoulli observed that this fraction is smaller than this fraction. Right? That is, 1 over n squared is less than 1 over the nth triangular number. Or if to say this is smaller than this, that means this denominator is bigger than this. This is the same as saying that n plus 1 over 2 is less than n squared. Right? So the question is this inequality true? So this inequality is equivalent to this, which is the same as saying that n times n plus 1 is less than 2n squared. And of course, this is n squared plus n. So if I cancel an n squared, this is the same as saying that n is less than n squared. And if I divide by n, that's the same as saying 1 is less than n. So for all n greater than or equal to 2, this inequality is true. So summation 1 over n, n plus 1 over 2 converges, implies summation 1 over n squared converges. Because these sums are less than these sums, and these sums don't go to infinity. They're bounded above. So these sums have to be bounded above. So this is proof by Bernoulli that the sum of the series converges, but he did not answer the question, what does it converge to? So the question is, converges to what? So this, in Bernoulli's time, was an open question. What does the series converge to? So this is the point at which chapter 8 ends, and the solution we find in chapter 9. So this is the end of chapter 8. Solution is in chapter 9, and it's due to the Swiss mathematician whose name is spelled Euler, and it's pronounced Euler. So Euler's solution to this problem is the great theorem in chapter 9. It really is a tour de force of 18th century mathematics, and it still is an extraordinarily impressive result. So the great theorem in chapter 9 is that summation 1 over n squared, n goes from 1 to infinity, for some miraculous reason is pi squared over 6. So this is a number theory problem. This is an arithmetic problem connected with squares. Pi we associate with a circle. So why the squares in the circle should be connected in this way is still a mystery. Okay. Any questions so far? So Euler somehow, again, we don't know what Euler did, of course. We can't ask him because he died 250 years ago. But you can look at this series, 1 plus a 4th, plus a 9th, plus a 16th, and just start literally adding up the terms and maybe writing them as decimals and see whether you get something, a number that you recognize. But very few people know what, I mean, pi, you think of as 3.14, whatever. Pi squared, I don't know, it's bigger than 9, but not as big as 10 probably, and divide it by 6. As a decimal, this is not generally familiar. So even working out a large number of, the sum of a large number of terms of the series might not even hint that the limit was equal to pi squared over 6. Right? But Euler somehow was able to perhaps guess this answer, and then, which is already very impressive, but then figure out a way to prove it. And he does this by starting with the trig function sine x. Okay. So sine x is this oscillating function. Y equals sine of x. It goes from -1 to +1, and it's 0 at every integer multiple of pi, and it's 1 at pi over 2 and -1 at 3 pi over 2. So this function is periodic with period 2 pi. That means that the sine of x plus 2 pi equals the sine of x for all x. If you know the graph of this function from 0 to 2 pi, it just repeats. You know it everywhere. And we also know that sine x takes on values between +1 and -1. And the only time the sine of x is 0 is when x is 0 plus or minus pi, plus or minus 2 pi. In general, plus or minus any integer multiple of pi. Those are the zeros of the sine of x. Okay. So in Calc 2, Math 176, you learned about Taylor series. Remember, a polynomial looks like a0 plus a1x plus a2x squared. Polynomial of degree at most n would just be a finite sum of n plus 1 terms up to like anx to the n. That's a polynomial of degree n. But if you just keep going forever, you have a power series. It's like a polynomial of infinite degree. You have all these different terms. And one of the things you learn in Math 176 near the end of the semester is how to write a Taylor, how to compute a Taylor series for a function. So for example, 1 over 1 minus x, that function is just, this is just the infinite geometric series for x in absolute value less than 1, for x between -1 and +1. This is one example of a Taylor series. Or e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial. The series goes on forever. The nth term is x to the n over n factorial. That's e to the x. And sine of x, which is what we use here, is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus x to the 11th over 11 factorial plus x to the 13th over 13 factorial. And you see the pattern. First of all, you only have odd powers of x to the power 1, 3, 5, 7, 9, and so forth. You only have odd powers of x. The signs alternate, plus, minus, plus, minus, plus, minus, plus, minus, and so forth. And the denominator of x to the k is k factorial. So x to the 3 over 3 factorial, x to the 5 over 5 factorial. So this is the Taylor series for the sine of x. And there's a nice formula for any Taylor series, but I'm not going to introduce it right here. But this is a way to write the sine of x as an infinite power series. Right? This goes on forever. Right? And this you see in the book on page 213. Any questions about this? Now, we use two facts about the sign of x in the proof of the great theorem. One is this Taylor series. The other is the fact that the zeros of the sign of x are the integral multiples of pi. So and for this, Euler used a fact about polynomials, which he extended to power series. So the fact that he wants to use is the following: that P of x be a polynomial of degree n with roots, I'll just denote them A, B, C up to D, and with the property that P of 0 is equal to 1. Then P of x can be written as a product of the form 1 minus x over A, 1 minus x over B, 1 minus x over C. There'll be n terms going up to 1 minus x over D. So let's look at an example of this. Suppose I take the polynomial, let's see, P of x equals x cubed minus 2x squared minus x plus 2. Now, if I let x equal 0, this gives me 2. So let me divide it by 2. So a half x cubed minus x squared minus a half x plus 1. So this is a cubic polynomial. That is, the degree of P is equal to 3. And I have also, if I plug in P of 0, I get 0 minus 0 minus 0 plus 1 is 1. So what are the roots? So let's see. Let me try to solve this. I want to solve a half x. I mean, I could use Cardano's formula, but that's really hard. So hopefully this will be easier. Half x cubed minus x squared minus a half x plus 1. I want to see what values of x will make this equal to 0. So from the first two terms, I could factor out an x squared. This is x squared times a half x minus 1 minus a half x plus 1 is minus a half x minus 1. Oh, that's good. Because if I factor out a half x minus 1, I get x squared minus 1. And this is easy now to solve. When is this equal to 0? When x squared is 1, so either x equals plus or minus 1, or a half x minus, so x squared minus 1 equals 0, when x is plus or minus 1, and a half x minus 1 is 0, when a half x equals 1, or x equal 2. So the roots of this polynomial are 1, minus 1, and 2. I just found the roots of this polynomial. So let me pause for a second and give you a chance to look at this to figure out what in the world I did and how I got here. Okay. Any questions about this? So solving finding the roots of this polynomial is just high school algebra, once you practice high school algebra a lot. And by Euler's factorization of a polynomial, so according to Euler, if this is correct, this polynomial can also be written as, see, what are A, B, and C? Plus 1, minus 1, and 2. 1 minus x over 1, 1 minus x over minus 1, 1 minus x over 2. Or if you like, 1 minus x over 1, 1 plus x over 1, 1 minus x over 2. And you can check that if you multiply this out, you get exactly the polynomial that we started with. If you multiply this out, this is what you should get. Actually, it's easy to check because 1 minus x times 1 plus x is 1 minus x squared. And if you multiply that by 1 minus x over 2, you get 1 minus x squared minus x over 2 plus x cubed over 2. And that's exactly right. So it does check. So the first ingredient in Euler's proof is the Taylor series for the sine of x. The next ingredient is based on the fact that a polynomial of degree n with p of 0 equal 1 can be written as this product over its roots. And
You said
let's see,
the product over what?
it's a product over the roots of the polynomial.
Oh,
Right, you have a factor 1 minus x over a for every root a of the polynomial. So this polynomial had roots 1, minus 1, and 2, and the product was 1 minus x over 1, 1 minus x over minus 1, 1 minus x over 2. The roots are 1, minus 1, and 2. So that's this factorization. Now let's just go back. Sine of x is x minus x cubed over 3 factorial, x to the 5th over 5 factorial, x to the 7th over 7 factorial, x to the 9th over 9 factorial, x to 11 over 11 factorial, and so forth. And it has roots 0, plus minus pi, plus minus 2 pi, plus minus 3 pi, and so on forever. But sine of 0 is equal to 0. It's not equal to 1. But Euler observed, if I take sine x and I divide it by x, I'm just taking one x out of every term of this. I have x over x is 1. X cubed over x is x squared over 3 factorial, which is 6. X to the 5th over x, I get x to the 4th over 5 factorial, which is 120, minus x to the 6th over 7 factorial, x to the 8th over 9 factorial, x to the 10th over 11 factorial, and so on forever. So if I call this function f of x, now what can I say? Well, in this case, if I let x equal 0, f of 0 is equal to 1. And the difference between this and this is that I factored out an x. So f of x has roots, not x equals 0 is not a root, f of 0 is 1, but its roots are the non-zero multiples of pi, plus or minus pi, plus or minus 2 pi, plus minus 3 pi, and so forth forever. And Euler intuited, or his intuition was, that just the way you could write a polynomial of finite degree as a product over its roots, you could do the same thing for a polynomial of infinite degree. So it should be that sine x over x is equal to 1 minus x over pi, 1 minus x over minus pi. Those are the first two roots. 1 minus x over 2 pi, 1 minus x over minus 2 pi. 1 minus x over 3 pi, 1 minus x over minus 3 pi, and so on forever. And of course, minus times minus is plus. So this is 1 minus x over pi, minus times minus is plus, 1 plus x over pi, 1 minus x over 2 pi, 1 plus x over 2 pi, 1 minus x over 3 pi, 1 plus x over 3 pi, and so on forever. And now the way these things are written, I can multiply them out in pairs, because 1 minus a times 1 plus a is 1 minus a squared. So the product of these first two terms is 1 minus x squared over pi squared. The product of the next two terms is 1 minus x squared over 4 pi squared. The product of the next two terms is 1 minus x squared over 9 pi squared. And this goes on forever. When you have 1 minus x over n pi times 1 plus x over n pi, you're going to have 1 minus x squared over n squared pi squared. That's the general term. But we have this infinite product, right? So this infinite product is equal to, what is sine x over x? This infinite product equals this infinite series. So we have an infinite series equal to an infinite product. The infinite series for sine x over x is 1 minus x squared over 6, 3 factorial, plus x to the 4th over 5 factorial, minus x to the 6th over, I'll just write it as 7 factorial, plus x to the 8th over 9 factorial, and so forth, equals this infinite product, 1 minus x squared, 1 minus x squared over pi squared, 1 minus x squared over 4 pi squared, 1 minus x squared over 9 pi squared. This goes on forever. The general term is 1 minus x squared over n squared pi squared. Just as in this series, for even numbers n, you're going to have x to the 2n over 2n plus 1 factorial. And this is minus 1. Let's see. When n is 1, it's minus. When n is 2, is plus. This is minus 1 to the n, x to the 2n over 2n plus 1 factorial. This is the nth term of the series. This is the nth term of the product. Okay? So in general, in mathematics, and this comes up in physics also some often, you have this very interesting phenomenon of an infinite series where you're adding an infinite number of terms is equal to an infinite product where you're multiplying an infinite number of terms. And that's what we have here. An infinite series equals an infinite product. Now, in this infinite series, the coefficient of x squared is minus 1 over 6, right? This is minus 1 over 6 times x squared. What is the coefficient of x squared here? Well, when do you get an x squared? So let's look at let's compute the coefficient of x squared in the infinite product. When you take an infinite product, you take a term from here times a term from here times a term from here and so forth. And if you're going to end up with an x squared, it means you choose one from all of these factors except from a single one of them. And in that single one, you're choosing minus x squared over n squared over pi squared. So you're going to get when do you get, what is the x squared term? It's going to look like minus 1 over n squared pi squared x squared for every n from 1 to infinity, right? You're going to get minus x squared over pi squared times 1 times minus x squared over 4 pi squared times 1 times 1 times 1 minus x squared over 9 pi squared. The x squared term in this infinite product is going to be this infinite series, which is, I can factor out x squared over pi squared and minus summation 1 over n squared, and goes from 1 to infinity. That's the x squared term. If I just want the coefficient, it's 1 over pi squared summation 1 over n squared. So in this right-hand side of this equation, the coefficient of x squared is this. On the left-hand side of this equation, the coefficient of x squared is minus a sixth. So therefore, so this is the important point. This is the coefficient of x squared in the product, minus 1 over pi squared, summation 1 over n squared, and goes from 1 to infinity. But on the right-hand side, the coefficient of x squared is minus a sixth. So if you multiply through by minus pi squared, you get summation 1 over n squared, and goes from 1 to infinity, equals pi squared over 6. And that's the theorem we wanted to prove. So Euler's proof that summation 1 over n squared is pi squared over 6 uses the Taylor series for the sine of x, and the factor is, and therefore the Taylor series of sine x over x, And the factorization of that is a product over the zeros of the function sine x over x. And equating the coefficients of x squared on both sides of the equation, we get the big theorem or the great theorem in chapter 9. Okay. Wow, that's pretty good. So you can play with this and get some other interesting results. So we just proved summation 1 over n squared, n goes from 1 to infinity, is pi squared over 6. So if you multiply by a fourth, 1/4 pi squared over 6 is 1/4 summation 1 over n squared, n goes from 1 to infinity. Let's see, pi squared, 4 times 6 is 24, so this is pi squared over 24, and 4 is 2 squared. So this is the same, pi squared over 24 is summation, n goes from 1 to infinity. If I bring this fourth inside, 1 over 2 squared, 1 over n squared. And 2 times n is 2n. So this is the sum of the squares of the reciprocals of the even integers, right? This is 1 over 2 squared, 1 over 4 squared, 1 over 6 squared, and so forth. That's pi squared over 24. Now, pi squared over 6, again, is summation 1 over n squared. That's the sum of the reciprocals of all the integers squared. And I can write this as the sum of the reciprocals of the odd integers. And the even integers, right? Here are the odds. And here are the evens. So it's the sum of the reciprocals of the squares of the odd numbers plus the sum of the squares of the reciprocals of the even integers. But this we just saw is pi squared over 24. So pi squared over 6 is this plus this, but this is pi squared over 24. So if I subtract summation 1 over n squared, n goes from 1 to infinity, but just over the odd numbers, that's pi squared over 6 minus pi squared over 24. That's a 6 minus 1 over 24 times pi squared. If you simplify the fraction as 6 minus 1 over 24, what do you get? What is 1/6 minus 1 over 24?
Um, 3/24.
Yes, which is?
Um, 1/6.
Can you simplify that, or is that reduced to lowest terms?
Negative 3 over 24 is no, 3 over 24 is the lowest it can go.
Let's see.
I-
Does 3 divide into 24?
Yes.
Yes, actually, yeah. I just realized because 24 is divisible by 6.
All right, so what is 3 over 24?
One over 8.
Yeah. So this is pi squared over 8.
It's the way you said it.
Why? I mean, 1/6 minus 1/24 is 1/8. That's 3 over 24, which is an eighth. So the sum over the reciprocals of the squares is pi squared over 6. The sum over the reciprocals of the even squares is pi squared over 24. The sum over the reciprocals of the odd squares is pi squared over 8. Let me just add one more thing.
Can you see that page? Can you see that page?
Yep.
Okay. I'm going to.
So we have summation 1 over n squared, n goes from 1 to infinity, is pi squared over 6. So this is the sum over the reciprocals of the squares, and it's natural to ask summation 1 over n cubed, n goes from 1 to infinity. What does that equal? Or summation 1 over n to the 4th, n goes from 1 to infinity. What does that equal? All right, and so on. And this, so I mean, if you're asking this, each of these series converges because this converges, and these terms are all smaller than 1 over n squared, so these series all converge. So it's a completely natural question to ask, what does it converge to? And Euler was able to show that 1 over n to the 4th is pi to the 4th over 90. Of course, then you could ask, what is summation 1 over n to the 5th? What is summation 1 over n to the 6th? Well, for summation 1 over n to the 6th, Euler could also figure that out. This turns out to be pi to the 6th over 945. You can ask, why is that what it is? And the answer is no one knows exactly. It depends what you mean by that, but that is the answer. And in fact, Euler could work out a formula for summation 1 over n to any even power. So for any even power, n to the 2k, n goes from 1 to infinity, this is some number, let me just call it b sub k, over times pi to the 2k, where this number, b sub k, is a fraction, a rational number. So for the even powers of numbers, the sums of their reciprocals, like the second power, the fourth power, the sixth power, and in general, any even power, we know exactly what the answer is. It's always pi to the 2k times a rational number. But what about 1 over n cubed or 1 over n to the 5th? So 250 years after Euler, we still don't know what these numbers are. This is one of the embarrassing open problems in mathematics. In fact, it was, I mean, you could conjecture that, for example, 1 over n cubed is a rational multiple of pi cubed, but no one knows how to prove or disprove that. And it was a very big deal not that long ago when someone could prove that this number is irrational, but not able to say much more than that. And the same for 1 over n to the 5th. So
Can you do 1 over 9th to the 8th?
sorry?
Can you do 1 over n to the 8th?
So, I mean, I could tell you what the answer is. But in this case, so this is some fraction times pi to the 8th, but this is sort of a complicated fraction, and if I write it down, it won't help you. You could get it in print, you can get it the same way we figured out pi squared over 6. You could look at this infinite series equals this infinite product. So in this infinite series, the coefficient of x to the 8th is 1 over 9 factorial. So you can multiply that out by hand, it's a big number. So x to the 8th, so the coefficient of x to the 8th is 1 over 9 factorial. How do you get the coefficient of x to the 8th in this infinite product? That's very complicated because you could get an x to the 8th by taking a product of 4x squared terms. But you can do that in lots of different ways, and you get some very, very, very complicated expression. And it's possible to find a closed form for it, but we're doing things in very elementary ways, and there's no elementary way to do that. If you look at a book in what is called analytic number theory, which means it uses a lot of analysis, which is advanced calculus and beyond, you can work out an expression for this number, right? But there just is no easy way to get it. You have to use what are called, or you use what are called Bernoulli polynomials, but yeah, I mean, it's been known for 200 plus years what these numbers are, but it's a lot more work to get them than one can do in a course like this. In fact, if you were trying to teach this in a course, it would probably be a month's work to get to an expression for the sum of the reciprocals of the even powers of n. But it is true there are always some numbers, some rational number times pi to the 2k, and this number involves something called a Bernoulli number, but we're not going to talk about that. I mean, I can give you a reference, but you have to know a lot of mathematics to be able to work your way through the reference. Okay. So it's always nice to know what is an open problem that would make you rich and famous if you solved it. And the open problem today is just the sum of the reciprocals of the cubes. What does that equal to? That really is an interesting question. Okay. All right. Let's continue with Euler's work. So Euler and number theory. So number theory is the study of just the positive integers. And Fermat in the 17th century discovered many, many, many beautiful properties of the primes, sorry, of the integers. And he usually didn't state them, didn't give the proofs. In fact, they didn't have research journals in the 17th century. A lot of scientific literature was simply done by one guy writing a letter to another guy saying, I can prove this, or I prove this, and I'm not going to tell you the proof. Let's see if you're smart enough to prove it yourself. So Fermat, Pierre de Fermat, who was a French lawyer in 17th century France, discovered many, many, many properties of the integers. And with one exception, they were all proven within, let's say, 100 years. But there was one result of Fermat that no one could prove for several hundred years, and it became known as Fermat's last theorem, because it was the last of the theorems he stated that no one could prove. So, and it's a generalization of the Pythagorean theorem. If you have a right triangle with sides A, B, and C, then A squared plus B squared equals C squared. So for example, and if A, B, and C are integers, like 5 squared plus 12 squared is 13 squared, right? This is a Pythagorean triple. This is a solution of this equation. Fermat's last theorem says for any n, so n is going to be the exponent. Here the exponent is 2. If you take any exponent 3 or greater, the equation a to the n plus b to the n equals c to the n has no solution in positive integers. So this was known as Fermat's last theorem, because from the middle of the 17th century until late in the 20th century, no one could prove this. But finally, it was proved by a British mathematician at Princeton named Andrew Weil. How does he spell his last name? Wiles. Wiles. Proved this around 1990 or so. I forget the date. But up until then, this had been the most famous unsolved problem in all of mathematics, Fermat's last theorem, because it's very easy to state. You have the Pythagorean theorem, which has a lot of solutions in positive integers. A squared plus b squared equals c squared. But a cubed plus b cubed equals c cubed has no solution. Or a to the 5th plus b to the 5th equals c to the 5th has no solution. So that for all n, for any n greater than or equal to 3, this equation has no solution. So this didn't become a theorem until 30 or 40 years ago at most. But for 250 years, everyone was trying to solve this. Euler proved many, I almost say most, of Fermat's claims. That is, Fermat claimed that certain things were true, and Euler proved them. So there is what is known as Fermat's little theorem. Fermat's little theorem says the following: let P be a prime number, then P divides a to the power P minus a for every integer a. Now, divisibility is tricky, so why should this be true? Let's look at an example. Fermat's little theorem. For P prime, A, any integer, P divides A to the P minus A. Let's look at some examples. Suppose I take P equal to 5. So let me make a table. Let's say here I have A, and here I have A to the 5th minus A. So, of course, when A is 0, this is 0 to the 5th minus 0 is 0. And 0 is 5 times 0, so 0 is certainly divisible by 5. If A is 1, 1 to the 5th minus 1 is 1 minus 1. Well, that's kind of silly, but that's also 0, which is 5 times 0. Suppose A is 2. 2 to the 5th minus 2 is 32 minus 2 is 30, which is 5 times 6, so that works. What about 3? 3 to the 5th minus 3. Let's see, 3 to the 5th. 3, 9, 27, 81, 243. 243 minus 3 is 240. It's certainly divisible by 5. It's 5 times 48. What about 4? 4 to the 5th minus 4. 4 to the 5th is 2 to the 10th. That's 1024 minus 4. That's 1020, which is certainly divisible by 5. That's 5 times 204. Now, this is interesting. What is 5 to the 5th minus 5? Let's see, what is 5 to the 5th? 5, well, of course, this is certainly, this is obviously divisible by 5 because I can factor out a 5. That's 5 times 5 to the 4th minus 1. So if I just want to check divisibility, that's enough. What about 6? 6 to the 5th minus 6. What is 6 to the 5th? I have 6, 36, 216. I'm going to cheat and open my computer because I don't have a calculator. I can't do. Six to the 5th is 7776. Minus 6 is 7770. I mean, anything that ends in a 0 is divisible by 10, so this is certainly divisible by 5. 5 times something. So that's okay. What about A equals 7? What is 7 to the 5th? Oops. Seven to the 5th minus 7. 7 to the 5th is 16,807, which is 16 minus 7 is 16,800, which is divisible by 10, so it's divisible by 5, and so forth. I mean, I don't know, let's take a random number, 13. What is 13 to the 5th? 371,293. But I subtract 13. And I get 371,280, which is divisible by 10, so it's divisible by 5, and so forth. So this is Fermat's little theorem. P divides A to the P minus A. Of course, A to the P minus A, if I factor out into A, is A times A to the P minus 1 minus 1. So if P divides a product of two numbers, if P is prime, it divides one of the factors. So if P does not divide A, then P divides A to the P minus 1. So this is an alternative statement of Fermat's little theorem. I like that one a lot, so let me write it down. If A and P are relatively prime, that means they have no common factor except 1, then that's the same as saying that P doesn't divide A. P divides A to the power P minus 1 minus 1. Let me just take a random example. Suppose I take P equal to 6 and A equal to 17. So this says that, sorry, P equals 6 is not a prime. Suppose I take P equals 7. So then this says that 7 divides 17 to the power 6 minus 1. So I want to use my computer. 17 to the 6th is 24,137,569. Subtract 1. I get 24,137,568. And if I divide that by 7, I get, this is, divides evenly, this is, I believe, 3, 4, 4, 8, 2, 2. Is that right? 17 to the 6 minus 1. That's 24,137,568. I claim this is divisible by 7. Let me just do long division if I can. This goes in 3 times. This goes in 4 times. This goes in 4 times. This goes in 8 times. This goes in twice. This goes in twice. This goes in 4 times evenly. Right? So this number is exactly 7 times 3,448,224. That's what it is. 3,448,224. That is Fermat's little theorem. So this is a fundamental result in number theory. And in fact, today, all of internet commerce is based on something called the RSA crypto system, right? If you buy something on Amazon, you give them your credit card and they charge your credit card. but anyone can steal your credit card number if it's being transmitted from your computer at home to Amazon. Well, maybe not anyone, but it's not hard to do. So the assumption is anything on the internet can be intercepted and read by anyone else. So if you send your credit card number 1234567, someone will intercept that, get your credit card number, your name, other, and steal your money. So when you type your credit card into Amazon, it doesn't send your credit card number across the internet. It takes your number and it encrypts it, it encodes it. It uses some secret code to change your number, and it sends the encrypted number. And if someone intercepts that internet communication, they don't know what your credit card number is, they just know what the encrypted number is. And if they can't break the code, they can't steal your money, right? That's the way it works. And it works not just when you're buying, a math book on Amazon, but when Chase Manhattan is transferring $1 billion to a bank in Switzerland, it's done exactly the same way. And when the US military is sending its plans for how to respond to a nuclear attack from Russia to a NATO ally, it's encrypted the same way. And this encryption is, as far as we know, unbreakable. And it's based on literally nothing more than Fermat's little theorem. So if you take a course in number theory, or for example, this summer, there's a course at Lehman in cryptography, you will learn how this all works. But it's very interesting that the basis of it, and you cannot have internet commerce without cryptography. It's impossible. You can't have international banking without cryptography. It's impossible. It's central to almost everything. And for the last 30 years or so, there is a system called RSA, named after three people, Rivest, Shamir, and Edelman. Rivest and Shamir were professors at MIT. Edelman was a graduate student. And Rivest and Shamir were always trying to come up with a new crypto system. And when they had an idea, they would talk about it in the coffee room at MIT. And Adelson was a kid who had nothing better to do than hang around in the coffee room all the time. So he started always trying to break whatever code Rivest and Shamir proposed. And he spent a lot of time on it. And when they finally came up with something that worked, they actually put his name on the patent. So all three of them became infinitely rich because they had the patent for this crypto system. But it literally is based on just Fermat's little theorem. It's quite fascinating. Anyway, I'll talk about I won't talk about cryptography more, but I will talk more about Fermat's little theorem and Euler's use of it on Wednesday. Okay. And that is all I'm going to say today, I believe. Any questions before we leave for the morning? Don't forget, beginning around 2:30 in New York, the moon will start to cover the sun, and it will have its maximum coverage around 3:30, because the moon is moving across the face of the sun. It'll start around 2:30. Around 3:30, it's at its peak, which is not 100% solar eclipse, but it's going to be pretty decent. And then it keeps moving, and it's going by 4:30. So it's fascinating, I believe, if you can see the solar eclipse, but you do not want to look at it. If you go, for example, to the New York Times, it describes how to construct a device to allow you to see the eclipse without damaging your eyes. And all it takes is 2 pieces of paper and a thumbtack or a needle to make a tiny hole in one of the pieces. It's utterly trivial too. You don't need to go and spend $2 at your local pharmacy to buy an eclipse viewing pair of glasses. In any case, they're probably sold out by now. But for two pieces of paper or 2 pieces of cardboard and a needle or a thumbtack or something for making a tiny pinhole, you can construct something to see the eclipse. And I know a lot of people are driving 3 or 4 hours north of New York. It's probably too late now, but to see the total eclipse. And they expect to have, humongous traffic jams of everyone going to where they can see the total eclipse. But a decent partial eclipse is visible in New York, at least if it's not cloudy and you're, somewhere where you can get to the sky. And it's worth trying to look at if you have a chance. Anyway, that's it for today. See you all on Wednesday morning.
All right. Thank you, Professor. Have a good day.
Thank you. You too. Bye all.